speed and frequency. So just because something's going fast doesn't necessarily mean that it's high frequency, or vice versa. Think of it this way. Maybe in chemistry, hopefully you learned about light. Light's an electromagnetic wave. And all electromagnetic waves travel at 3 times by 10 to the 8 meters per second through space in a vacuum. And the frequencies of those electromagnetic waves can be very different. We can have increased or decreased number of wavelengths that occur within the same amount of time or that cover the same amount of distance. And so we could have high frequency with the same speed or low frequency with the same speed, okay? So that's similar concept here. We can be traveling at the same speed with lots of little waves in there, or you travel at the same speed with longer, wider waves. And so that would be the frequency component of it. All right, now here's one correlation that something I'm sure you've seen and experienced before is listening to the radio. And what we see is that these radio waves typically, I believe they cause the electrons in the antenna to vibrate, and they vibrate at certain frequencies. And so that we can determine and use different frequencies to hone in on different radio stations, okay? So let's talk through kilo and mega. So AM radio waves are broadcast in kilohertz. So kilo, 1,000, right? There are 1,000 hertz in 1 kilohertz. Let's put that conversion factor down here. So there are 1,000 hertz in 1 kilohertz, okay? So if we have 120,000 hertz, okay? 120,000 hertz. That would be the same thing as 120 kilohertz. Or for this particular frequency, that would be 120 AM radio. That's the station. Okay. Now FM, different, slightly, megahertz. Okay, so mega is 1,000,000. So there are 1,000,000 hertz in 1 megahertz. Okay, and so a station here in St. George that we run into all the time is Coney Country, right? And so that one is 99.9 FM. Okay, so let's determine what that would be. So that would be the same. Let's see, FM is megahertz, right? So it'd be 99.9 megahertz, which is the same as 99.9 million. I wonder if I'll be able to fit all those zeros in. Million hertz, right? All right, keep going. All right, here's the first equation. It's this relationship between period and frequency, okay? And so period is equal to 1 over frequency. how could we rearrange this equation to solve for frequency? Okay, so we want to get frequency by itself instead of period. Well, frequency is on the bottom of the fraction, so how about we multiply that to both sides? So you'd have frequency multiplied by time, and then it would cancel over here, so that would all equal 1. And then you could divide by the period to get frequency all by itself. So a rearrangement of this same equation, you could say frequency is equal to 1 over period of the wave. Okay? Remember, unit of period is in seconds, the amount of time it takes for one complete wave to occur or pass a given point. And then frequency is measured in hertz, right? We talked about that quite a bit. And frequency is per time. And look, that makes a lot more sense now because we know that period is represented in seconds or time, and frequency is per time, right? And so reminder, hertz in particular is per second. There's a couple different ways we have of writing that, and they all mean exactly the same thing. Okay. And then this equation is the wave speed equation, and we're going to come back to this in a moment because there's a rearrangement of this that we're going to do. So let's look at our example problem number 1. Okay, a radio wave has a frequency of 2 megahertz. Calculate the time period between these successive waves. And then example number 2, a radio wave vibrates an antenna with a period of 1.001 times 10 to the negative 8 seconds. What is the radio station? Okay, we're going to solve for frequency. So what I want you to do is use this equation up here and use your info that we know about radio waves for example number 2. So I want you to hit pause, give these a go, and then when you finish, hit play again, and we will talk through them. See how you do. Okay, radio wave has a frequency of 2 megahertz. So I'm going to make a list of what we know, and I'm going to decide what equation I'm going to use, and then see if I need to rearrange that equation. So we know that frequency is 2 megahertz, okay? And a megahertz is the same thing as a million, so that could be rewritten as 2 times by 10 to the 6 hertz. And we want to calculate the time period between successive waves, the time it takes for a complete wave to occur. So that would be the period of the wave. So that's what we're solving for. Okay, so we're given the frequency, we want to solve for the period. So we need to find an equation that we know all the information except for what we're solving for. Okay, and so when I look at this, we haven't been given the wavelength or the velocity. We have been given the frequency, and we're asked to solve for the period, and 1 is part of the equation. We know what that is, and so this would be a great equation to use because we know everything except for the unknown. So we're going to use the equation period is equal to 1 over frequency. Okay, something that's important to note that some of us I think are struggling with is we have to be really careful when plugging in fractions into our calculator, especially if we have numbers with scientific notation. And so here we're going to take 1 divided by the frequency. And if you just put in 2 times by 10 to the 6th, what your calculator will do, depending on the calculator, see, we got 2 very different numbers there. Okay, so let's talk through what's happening. If you forget to put your parentheses in, like I did the first time on the bottom of the equation, what happens is your calculator will go 1 divided by 2 first. It'll run that number, and then it'll take that number, 0.5, and it will multiply it by 10 to the 6th, right? But here we say, no, I want this number to be entirely on the bottom. I want the calculator to run that first. So this way it goes 1 divided by this entire number, which is something very different. 5 times by 10 to the negative 7th. And so that is the correct way to approach this problem and plug it into your calculator. We have 3 significant figures right there. So we're going to have 5 times by 10 to the negative 7. And this is period, which is measured in units of seconds. And if we've forgotten that, but we do know that frequency is in hertz or inverse seconds, we can prove this. We can do a unit analysis, right? We can do 1 divided by hertz, right? Frequency, which is in hertz, and that's the same as inverse seconds. And we know that anything, when you divide by a fraction, it's the same as multiplying by the reciprocal there. And so 1 multiplied by seconds over 1, which would just be seconds. Example problem number 2. A radio wave vibrates an antenna with a period of 1.001 times by 10 to the negative 8 seconds was the radio station. So we know that the period is equal to 1.001 times 10 to the negative 8 seconds. Okay, and we have a little hint here. We're going to solve for the frequency first. That's what we're going to look for. And so again, here this equation, we know the period, we know 1, and so that's our only unknown, and that's what we're solving for. And we've already taken a moment earlier to rearrange this. So we're going to do frequency is equal to 1 over the period. Okay, so I'm going to plug that in my calculator. 1 divided by 1.001 times by 10 to the negative 8. Notice I've put it in parentheses, telling my calculator to keep all that below. We get 9.99001 times 10 to the 7th there. Four sig figs times by 10 to the 7th, and this is frequency, which is hertz or inverse seconds, right? 1 over seconds. So that'd be hertz. Okay, now how can I figure out the radio station from this? We could take this either direction, but we know that this is times 10 to the 6th, and this is times 10 to the 3rd, and so we're a lot closer to this idea than we are to that, right? Like 9.990 times 10 to the 7th, that's the same thing as 99.90 times by 10 to the 6th, or a million, right? 99.90 million hertz or megahertz. 99.9 megahertz. And megahertz, FM radio is measured in megahertz. So that must mean that this is 99.9 FM. Okay. Wonderful.